This video will lead us through the answers and problem solving for the very first kitchen sink free response assigned question. The primary author is a teacher, a Mr. Melican, and so we just honored that with the designation of Melican Question 1 in the title. This video will remind us of the actual question, provide my answers and sample problem solving, as well as a created predicted scoring guide. And then I'll go through the reasoning of the problem solving. So please feel free to pause the video, skip ahead, to just get the parts that you actually need to be able to master and earn all the points for a question like this. So let's dig in first to being presented the question. Now, as I place this on the screen, if you want to pause to get parts A and B, then I will move this up so that we can focus on the data table and then C through G. And then the last part of this question, H and I. Now, my answers and sample work, or the answers and sample work, I will go through the scoring guide so you can kind of ignore the point designation, but there would be A, B, 40.7 milliliters of the silver nitrate solution, the answer for C, the answer and my work for D and E, for F, for G, you just needed to have one possible reason. Another reason could have been spilling of some of the precipitate that was collected from the filter paper. This is a little bit of a weaker, because you were told in the beginning that you added a sufficient amount of the silver nitrate solution. Part H, we need to make sure we can get the correct Lewis dot structures to understand the number of bonds that we are breaking and making. I ran out of room on my single page, so the answer to H is 475 kilojoules per mole. And then part I asks for the resonance structures and then a justification as to the bond energy within nitrate. All right, I will just display for you the scoring guide that was created. This far box in the right is where you can jot down your score. As long as you had the correct species in the net ionic, you would have gotten the points without phase symbols. For B, a point would be earned for showing the correct mole-to-mole ratio somehow in your problem solving of silver chloride and silver nitrate. And then an additional point for the correct answer with, of course, correct units and sig figs. Remember, no work, no credit, no point. I know that some of this is a little scratchy and fuzzy, so I just rewrote my answer. C, moles 0.0513, you would get 1 point for the correct data that you subtracted, an additional point for converting between grams to moles. You, ladies and gentlemen, again, if you made an error here, but then did this part properly, even though you don't have the right answer, you would earn this point. And then the same thing continues on, where if you needed to reuse this number and this number was an error, you would still get the credit, even though numerically you don't have the right answer, if you problem solve correctly. So the same thing here as earlier, you would get 1 point for recognizing the correct mole ratio between the silver chloride and sodium chloride, and then using formula mass to get your right answer. And then for E, it's setting up the correct ratio of grams of sodium chloride to grams of mixture, multiplying by 100% and getting the correct answer. But again, if any of these numbers, if this number from earlier was erroneous, you would still get the correct point if you divided by the mass of the mixture. Okay, part F, you need to address something about heating to constant mass. G, one reason. H, and I'll go through my problem solving, you would get 1 point for bond energy of reactant minus bond energy of product, or just numerically assigning correct signs or interpreting this equation. Now remember, this equation is not on our equation sheet, so we want to be careful that we remember that. You would get an additional point for interpreting this correctly, that every nitrate would have 1, 2, 3 of these resonating bonds, but you're making 2 molecules of it. So that's a total of 6 nitrogen-oxygen resonating bonds, and then correct answer. For I, you would get 1 point for the correct Lewis dot, showing the alternating double bond. Of course, the order does not matter. And then 1 correct point for making the correct justification of where the resonance bond energy that you were given compares to single and double. Now, I created this scoring guide, and we know that free response questions are usually 4 or 10 points, but this is a little bit more lengthy of a sample question, and so I think this is definitely a reasonable point attribution out of 15 points. And if we are delivering an 80% correct, we are in great standing. Okay, so to talk through the reasoning of the problem. So I'm going to go through step by step how I tackled it. If just sharing the answers is sufficient, then you are set. All right. So make sure that we are forcing ourselves to take our time and read every part of this problem. Okay, the student has a mixture of sodium chloride and sugar. I'm a writer-downer as I problem solve, so I'm probably going to make a note. Okay, sodium chloride and sugar. Okay, I'm already kind of in my head thinking, okay, this is just going to be white because these are white crystalline. This is ionic, this is covalent. I wonder where I'm going with this. Okay, to determine the percent comp, the student measures out, 5.84 grams of this mixture. So this has both compounds in it, and then dissolves. Okay, I know both of those are soluble in 100 milliliters of water. Okay, so I have a solution. Now I know that my sodium ion and chloride ion will dissociate. That's what ionic compounds do, but my sucrose will not. All right, but this will be clear and colorless, completely soluble, especially that small amount in that amount of water. Okay, the student knows aqueous sodium chloride will react with silver nitrate. Okay, so sodium chloride will react with silver nitrate to form solid silver chloride. All right, well, this is a double replacement reaction, so my other product, sodium nitrate. I might need that. The student determines the sugar will not react with the silver nitrate. Okay, this is the only thing it's going to react with. All right, a balanced net ionic. All right, so this will be dissociated. But remember, all nitrate compounds are soluble, so this will be dissociated. Okay, +1, -1, +1, -1. So when they exchange their ions, I'm good on these formulas and the balance equation. Okay, but we know that this insoluble will not be markedly dissociated, and so I should write this together, and then my sodium ion and nitrate ion will be dissociated. So which are my spectators? My sodium and my nitrate. Now, these are soluble. And so, even though you'll get the point without showing phase symbols, I'm going to, because I want to show I know my chemistry. Okay, that's our answer for A. Now, I know I wrote a lot here, so I want to make sure that the scorer can see my answer, and I've written it dark enough, and I definitely have shown these ion charges. You would not get credit if those ion charges were not there. Okay, how many milliliters of 1 molar silver nitrate would be required to precipitate 5.84 grams of silver chloride? All right. So, even though that's the mass of the mixture, all right. So what they're saying is, okay, we want to precipitate all of the 5.84 grams of silver chloride. All right. So if I think, okay, that's what I'm hoping to get. Okay, the question is, I'm using 1 molar silver nitrate. Now, I know I can write 1 molar silver nitrate as a conversion factor. And so that's why I chose to start with my mass of product. Okay. Now, I need milliliters of this at the end, so I'm probably going to use, of course, molarity to get me there in some way, shape, or form. So I'm going to keep in mind, I want for my answer milliliters of this silver nitrate solution. Well, this is going to get me liters, and I need to be in terms of moles of silver nitrate. Okay, so if I look back at my reaction, this is my product. I have 1 mole of this for every 1 mole of this reactant, and the source of this is the silver nitrate. All right, so let me first get myself from grams to moles of this guy. And it's 143.32 grams of silver chloride in 1 mole. Make sure that you're going to the 100th place. And I know per my reaction that every 1 mole of silver chloride that reacted, I needed 1 mole of the silver ion. And 1 mole of silver ion is in every 1 mole of silver nitrate. All right, so look where I am now, da-da. All right, so I know 1 mole of silver nitrate from the given molarity is in 1 liter of the silver nitrate solution, and 1 liter of silver nitrate solution is 1,000 mils. Okay, sig figs. So this 1 molar, limits us to 2. I don't think I saw that when I first worked out my key, yike. This would limit us to 3, this limits us to 5. So actually, ladies and gentlemen, this should be 41 milliliters of silver nitrate solution. And I want to make sure that it's clear what my answer is, so I'm going to circle that. Okay, so then it talks about, all right, some data we're given. So we have the filter paper, and I imagine this is just the piece of filter paper with nothing else on it. Okay, this is when I collected the precipitate, dried it, masked it. Then I probably let it sit a little longer, or maybe I applied some gentle heat, maybe put it in a warming oven, masked it again. But I want to make sure that all of the water that is still in the precipitate has been driven away. So I probably masked or heated a little longer. Remember, we want to heat until our mass doesn't change more than 0.01 gram if we can. Then we're heating to constant mass. We've driven all of the water away, says our data. All right, how many moles of silver chloride were precipitated? Well, that's what we collected, right? So our reaction made this, and this is what's in our filter paper, this precipitate. So how do I find out how many moles? Well, I want to use my final massing. And I know we might be torn. Okay, do we use this or do we use this? So why don't we use the 8.55 gram of the collection, and subtract from that the mass of just the filter paper. So this is the precipitate in the filter paper. This is just the filter paper, and I should get 7.36 grams. Right? Oh, 7.34. I knew I was erroneous in that, ladies and gentlemen. I'm so sorry. So 7.34 grams, and that will be of the silver chloride. But it's asking for how many moles. So, using the formula mass again, and I get, now, this 3 sig figs, remember when we subtract, we want the least precise decimal place, but this gives me 3, so then dividing out, 0.05, oh shucks, with my correction, I have 0.0512 moles of silver chloride. Okay, then, well, how many grams of sodium chloride were present in the original mixture? Well, remember, the chloride that's here came originally from the sodium chloride. All right. So, if this is what I ultimately collected, well, if I go back to my original chemical equation, for every 1 mole of this, well, that came from 1 mole of chloride, and the sodium chloride was the original source. So, I'm going to go ahead and show that every 1 mole of silver chloride, well, that needed 1 mole of chloride to make that. And for every 1 mole of chloride, that's 1 mole of silver, or a sodium chloride. If you just had these on top of each other, you would earn the credit, of course. And then we have to get ourselves to mass, which sodium chloride, of course, is 58.44 grams. Let me just double check my math. And 2.99 grams of sodium chloride. Okay, what is the percent of sodium chloride in the mixture? Well, a mass percent will be the mass ratio of the part compared to the whole. So we were told that the original was 5.84 grams. Part compared to the whole times 100. And with my correction, 51.2% sodium chloride in the mixture. Okay, part F. So, why did the student dry and mask the precipitate? 4 times. So, to ensure all water was driven from collected precipitate, the precipitate and filter paper were heated to constant mass. That probably is sufficient to answer the question, but we could say when a mass difference of plus or minus 0.01 grams was obtained between the third and fourth heating, data supported all water removed. Again, probably that would be sufficient. Okay, part G, rather. So you found that the experimental percentage was less than the actual percentage. Okay, so if this is how we found the percent, we know that that was accurate. So to get a lower value than we should have, we must have lost some of our collected precipitate. So where would we have lost it? Well, you only have to give one reason, and a reason could be that some of the collected precipitate fell from the filter paper, which shame on us, but we know how easy that is to happen. Maybe when the precip was filtered, the solution overran the filter, allowing some of the precipitate to not be filtered. So if you could imagine that, you have a collection beaker, and if you fill your funnel too full, and here's where your filter paper is, and it can actually run behind, and that doesn't go through the filter. Again, a reason I cited before could be that we didn't add enough of the initial solution, the silver nitrate, to precipitate all of the chloride ion, but you were told that you added enough until you didn't see any more precipitate. So I think that these are probably the most acceptable responses. Okay, so part H, what you needed to do was to realize that in this reaction you are breaking one nitrogen-nitrogen triple bond, and if we needed a hint, look at the bond energies you're given, and we would be breaking 3 oxygen double bonds, just to respect the lone pairs, and then we are making nitrate. Now, nitrate. So we're going to start by assigning nitrogen 6 valence electrons. All right. And then it's being bonded to 3 oxygens. Now we know each oxygen brings in 6. Now, nitrogen and oxygen never exceed the octet rule. So how do we get our bonding? Well, the nitrogen needs 2 more to have its octet satisfied. So why don't we double bond with this first oxygen using 2 lone pair, or 2 electrons from oxygen, 2 electrons from nitrogen. Well, then this has its octet and your nitrogen has its octet. So what will form, remember these are called coordinate covalent bonds. Nitrogen will donate the pair, oxygen will keep its 6, and everybody's content. But I chose to make the double bond here. Someone else may have chosen to put it here or put it here. That's proof that this is going to resonate. Okay. I just have to find what this bond is. Now, we know that this will be taking turns between the 3 oxygens. So really, overall, the bond length will be like 1 1/3. This double bond is being shared between 3. All right, we're being asked to find what that bond energy is. I am making 3 oxygens and 2 of the nitrates. Okay, now the enthalpy of your reaction is a sum of the bond energies of reactant minus the sum of the bond energy of product. Okay, so this is what we're trying to find. You were told through this reaction what the enthalpy of the reaction is. -414 kilojoules per mole of reaction. Okay, I am breaking all of these bonds. So I am breaking 1 mole of nitrogen-nitrogen triple, and that's what this bond energy represents. Remember, bond energies are always positive because they are amount of energy that must be invested to break the bond. And I will add that to, now I am breaking 3 of these oxygen double bonds. And that is 498. Okay, and I will subtract from that. Now, I'm making 2 molecules, and I'm going to be forming each of these. So that gives me 3 times 2, that is 6 moles of the nitrogen-oxygen resonating bond. So I'm going to put a ... there, because it's a single, and then what would be a third, and this is my X. This is what I'm trying to find. Now, remember, these are positive. Bond energy is the energy invested, but when that bond forms, it's going to be released. That's why we make that negative. So be careful with your algebra, and then what we end up getting is that 475. And remember, bond energies are positive. Positive. And if we take a look, it's a reasonable value that we're getting looking at a triple bond between nitrogens and a double bond between the oxygen. Okay. Then it asks for, explain why the value that you just got is between what would be a single bond between nitrogen and oxygen and a double bond. Well, you know that a single bond versus a double bond, this has a lower bond energy and is longer. This has a higher. Well, why is what you got between this? Well, if I go back to show you my answer, well, here we want to just show the resonance. You don't have to show any kind of correct geometry. Just showing, and it doesn't matter the order, where you alternated your double bond. But then, because the oxygen is alternating between 3 oxygens, it will be like 1 1/3 of a bond. And so I think showing where it falls between the different bond energies that you're given would be a really strong way to answer this. If you have questions and concerns, please directly email your teacher, and I surely hope you secured that 80% on this question.